Welcome to our Quantum Deep Dive.
Great to be here.
Today we're diving deep into a field that, well, it basically lets us listen to matter at its most fundamental level, quantum spectroscopy.
It's a fascinating area.
And our guide for this exploration is an excellent essay, Quantum Spectroscopy, Precision of Atomar Ebene, by Yorgo Schneepat.
A really insightful piece.
So our mission today is pretty straightforward but deep. We want to unpack what this powerful tool actually is.
Yeah, to the heart of it.
Exactly. Understand its quantum core, see where it came from, what amazing things it lets us do now, and maybe peek at the revolutionary paths it's opening up for the future.
Sounds like a plan. Where should we start?
Let's just kick off with the core idea. What is quantum spectroscopy?
Well, fundamentally, it's about looking at how light and matter interact. But crucially, it does this through the lens of quantum mechanics.
Okay, so not just classical optics.
No, it's deeply quantum. The goal is really to understand the properties of atoms, molecules, even solids, by analyzing their spectral signatures. Think of them like unique fingerprints.
Fingerprints made of light.
In a way, yes. These signatures come from energy transitions. See, quantum systems can only exist in specific, discrete energy states.
Right, quantized levels.
Exactly. When they absorb or emit light, they jump between these allowed states. The energy or color of that light corresponds exactly to the energy difference between the states. That's what gives us those sharp spectral lines we analyze.
And how does this quantum approach really go beyond, say, older methods?
Well, at the microscopic level, things get weird, Quantum effects like superposition, where a system can be in multiple states at once, or nonlinear effects, where maybe two photons interact simultaneously, these become really important.
The things classical physics doesn't really account for.
Right. And quantum spectroscopy embraces these effects. It allows us to study physical and chemical processes with just incredible precision, down to the atomic or molecular scale.
It sounds like its history must be tightly woven with quantum mechanics itself.
Absolutely. You can trace its roots right back to the early 20th century. I mean, the whole idea started with Max Planck. That's the one. The concept that energy comes in discrete packets or quanta, that was fundamental.
And Einstein played a role.
A huge one. His ideas about stimulated and spontaneous emission weren't just theory. They were the bedrock for inventing the laser decades later. And you really can't do modern spectroscopy without lasers.
Okay.
Then you had Niels Bohr figuring out the hydrogen atom structure and explaining its specific spectral lines as these quantum jumps between electron orbits.
So linking the theory directly to the observed spectra.
Precisely. And of course, the developers of quantum mechanics itself, like Schrödinger with his equation, Heisenberg with matrix mechanics, they built the theoretical framework that underpins the whole field.
And more recently.
Well, the field has just exploded, really.
Yeah.
Driven by huge advances in laser technology and the broader field of quantum optics. We have amazing control over light now.
Okay, so we have the what's and the how it started. But the big question is always, so what? Why is this precision, this quantum view, so important today? What does it actually let us do?
That's the key, isn't it? It provides this vital experimental link to quantum theory. Those precise spectral measurements we get, they aren't just abstract lines.
They're data.
Exactly. Data that lets us pin down fundamental properties. Things like the exact energy levels in an atom or molecule, the probability of it jumping between states, even how different parts of a system are coupled or interacting. It's essential for really understanding the microscopic world.
You mentioned the time-dependent Schrödinger equation earlier. How does that fit in?
Yes. Well, that equation basically describes how a quantum system's state changes over time. In spectroscopy, we're often watching how these states evolve, maybe after we've zapped them with a laser pulse.
So the theory helps interpret the experiment.
Directly. We need that equation to make sense of the dynamics we observe in the spectra.
And the applications seem incredibly wide-ranging.
Oh, they really are. I mean, in chemistry, it's indispensable for figuring out molecular structures, bond angles, how electrons are arranged, even watching reactions happen step by step.
Wow.
Physicists use it to study really exotic stuff like Bose-Einstein condensates matter cooled near absolute zero or strange new materials.
Like superconductors.
Superconductors, topological materials, yeah. Material scientists rely heavily on it to characterize these new substances.
And its role in quantum technologies. You hear so much about that now.
It's crucial, foundational, really. For building quantum computers, you need to know the precise quantum states of your qubits. Spectroscopy gives you that information. Same for developing components for quantum communication.
Could you give a specific example, something that highlights the quantum aspect?
Sure. Take two-photon spectroscopy. Normally you shine light, and if the energy matches, one photon gets absorbed, causing a jump.
Right.
But with intense laser pulses, you can actually make an atom or molecule absorb two photons simultaneously. The total energy is the sum of the two.
Okay. Why do that?
Because it lets you access energy states that are forbidden, inaccessible, with just single photons. It opens up different selection rules and reveals different information, especially about nonlinear interactions between light and matter. It's a purely quantum effect being exploited.
Okay, let's dig a bit deeper into the quantum rules then. We've got quantized energy via the Schrödinger equation. What else is key?
Well, the Heisenberg uncertainty principle is definitely relevant.
Can't know position and momentum perfectly.
That's the classic version. In spectroscopy, it often manifests as a trade-off between knowing the exact energy of a state and how long that state lasts, its lifetime. Shorter lifetime means a broader, less precisely defined energy level, which you see as wider spectral lines.
I see. And molecules.
Yeah.
They're more complicated than atoms, right? More ways to store energy.
Oh, much more complex. You have the energy tied up in how the electrons are arranged. Those are the electronic states. Transitions between these typically involve UV or visible light. But the atoms within the molecule can also vibrate, like masses on springs. These vibrations are quantized to vibrational states. That's usually in the infrared region.
And they spin around.
Yep, molecules rotate. And guess what? Those rotations are also quantized. Rotational states? You typically probe those with microwave radiation.
So a molecule's total energy state is a mix of all three: electronic, vibrational, rotational.
Exactly. And spectroscopy can be designed to look at transitions involving just one type, or sometimes combinations, depending on the light you use and the technique. It gives you different pieces of the puzzle.
So how does the light actually interact? How does it read these states?
Fundamentally, it's about energy exchange between the electromagnetic field, the light, and the matter. The main ways this happens are absorption.
Where a photon gets soaked up, causing a jump to a higher energy state.
Right. Then there's emission, where the system drops to a lower state and spits out a photon.
Like fluorescence.
Or phosphorescence, yes. And finally, scattering, where the light interacts, bounces off, essentially, but isn't fully absorbed or emitted. It just changes direction.
Right.
Maybe losing or gaining a tiny bit of energy in the process.
And what determines if a particular jump, a transition, will actually happen when light shines on it?
That comes down to something called the transition dipole moment. It's a quantum mechanical calculation, basically.
Right.
It measures how strongly the light's electric field can couple the initial state and the final state. If that calculated moment is 0 for a particular pair of states,
the transition is forbidden. It won't happen.
Under the usual rules, like electric dipole interaction, yes, it's highly unlikely. This is incredibly important.
That leads to selection rules.
Exactly. These rules pop out of the quantum mechanics and the symmetries involved. They tell us which transitions are allowed and which are forbidden based on changes in quantum numbers. For example, a common rule for vibrations is that the vibrational quantum number of V's can only change by plus or minus 1. Delta V equals plus or minus 1.
So the rules explain the pattern of lines we see.
Precisely. They dictate the structure of the spectrum, why certain lines are strong, others weak, and some completely absent. They're crucial for interpretation.
Right, let's talk tools. What's actually in the spectroscopist's lab? What methods do they use?
Well, the modern toolbox is pretty sophisticated. Laser-based techniques are absolutely central.
Like basic absorption and emission spectroscopy.
Yeah, those are the fundamentals, measuring how much light gets absorbed or emitted at different frequencies. And lasers are key here because they give you light of a very specific color monochromatic, and the waves are all in step coherent.
Which lets you target specific transitions very precisely.
Exactly, selective excitation.
What about Raman spectroscopy? That's laser-based too, but different.
It is different. It relies on that inelastic scattering we mentioned.
Where the light swaps a bit of energy with the molecule.
Right. Most light just scatters off with the same energy. But a tiny fraction interacts with the molecular vibrations, gains or loses a bit of energy. The frequency of the scattered light is shifted slightly.
And that shift tells you about the vibrations.
Exactly. It tells you the vibrational frequencies of the molecule.
What's the advantage of Raman sometimes?
One big one is water. Water absorbs infrared light really strongly, which makes standard IR vibrational spectroscopy tricky for biological samples or anything in solution.
But Raman doesn't have that problem.
Generally, no. Water has a weak Raman signal. So Raman is great for studying things in water, like cells or proteins, and often needs very little sample prep. You get detailed chemical info.
You also mentioned nonlinear techniques earlier, like the two-photon example.
Yes, nonlinear quantum spectroscopy. This involves processes where multiple photons interact with the sample simultaneously or in very quick succession.
Needs powerful lasers, I guess.
Typically, yes. Intense, often ultra-short pulses. Think femtoseconds short. Two-photon absorption is one example, but there are others, like coherent anti-Stokes Raman scattering, or CARS. These methods can probe different aspects of the system, often giving higher sensitivity or accessing information hidden from linear one-photon techniques.
And theory isn't just background. It's an active tool.
Oh, absolutely essential. Quantum chemical calculations using methods like DFT, density functional theory, or Hartree-Fock are used all the time.
To predict what the spectra should look like.
Exactly. You can calculate the electronic structure, the energy levels, using the electronic Schrödinger equation, and predict the spectrum. Then you compare it to the experiment.
So it helps figure out what you're actually seeing.
Definitely. Simulating spectra is crucial for interpretation. You can calculate those transition dipole moments, predict vibrational frequencies, model how the molecule's environment might shift the spectrum using molecular dynamics. It's really a partnership. Combining theory and experiment gives you a much, much richer picture.
Okay, let's zoom in on the impact. How is this cool kit actually changing things in, say, chemistry and materials science?
It lets us see the nuts and bolts. We can analyze chemical bonds directly, lengths, angles, electron distribution by looking at the electronic and vibrational signatures. It's fundamental chemistry.
Can you actually watch reactions happen?
Yes. With time-resolved spectroscopy, you use pump probe techniques. One ultra-short laser pulse starts the reaction, pump. Then another pulse, delayed by a tiny amount, probes the state of the system, the probe.
And by changing the delay.
You build up a movie. You can literally track ultra-fast processes like bonds breaking or forming on femtosecond timescales. It's incredible.
And for new materials.
Indispensable. Characterizing semiconductors, superconductors, nanomaterials. Spectroscopy gives you the vital fingerprints. For example, resonance Raman is amazing for studying materials like graphene. You can see defects, strain, the electronic band structure, things crucial for its applications.
What about the life sciences? Biophysics and medicine.
Huge impact there too. Techniques like fluorescence spectroscopy are workhorses for studying proteins, DNA, cell membranes, how they fold, how they interact.
You mentioned FRET before, Versatile Resonance Energy Transfer.
Yes. It's a really clever technique. You label two parts of a biomolecule with different fluorescent dyes. If they get close enough, energy can transfer non-radiatively from one dye, the donor, to the other, the acceptor.
And the efficiency tells you the distance.
Exactly. The efficiency drops off really sharply with distance like 1 over r to the 6th power. So it acts like a molecular ruler, measuring distances on the nanometer scale within or between molecules. Super useful for studying conformations.
And more direct medical uses.
Yeah, there are exciting diagnostic applications emerging. Near-infrared spectroscopy, NIRS, can shine light harmlessly through skin and tissue to monitor things like blood oxygen levels. Non-invasive. And Raman spectroscopy is showing real promise for cancer detection. Turns out, cancerous tissue often has slightly different molecular composition than healthy tissue. Raman can pick up those subtle spectral differences, potentially allowing for faster, more accurate diagnosis, maybe even during surgery.
Wow. Okay, and finally, let's connect it back to quantum computing and communication. How does spectroscopy feed into those fields?
It's absolutely fundamental for building the hardware and understanding the systems. For quantum computers, whether you're using trapped ions, superconducting circuits, or quantum dots as qubits, you need spectroscopy to measure their energy levels precisely, check their coherence times, basically characterize the very things that make them quantum.
So quality control for qubits.
In a sense, yes, and the data itself is useful. Spectroscopic data on molecular energy states is used as input for quantum algorithms, like the variational quantum eigensolver, or VQE, which aim to simulate molecules on quantum computers, one of the big potential applications.
And for quantum communication, sending quantum information.
Crucial there, too. Developing things like single photon sources or sources of entangled photons relies heavily on spectroscopy. You need to characterize quantum dots, defects in diamond, optical resonators. Optimize them for emitting the right kind of quantum light. Single quantum dot spectroscopy, for instance, lets you measure exactly how good a potential source is, its coherence, efficiency, entanglement properties.
Looking ahead then, what's driving the field forward technologically, and what are the big hurdles?
While technology is always pushing the boundaries, new light sources are a huge deal. Things like free electron lasers, FELs,
What's special about them?
they produce incredibly intense, coherent beams of light, tunable over a massive range, from infrared way up to X-rays. And crucially, they can generate ultra-short pulses down to femtoseconds or even less.
So you can see really fast processes.
Exactly. Study ultra-fast dynamics, watch electrons moving, probe atomic structures with unprecedented clarity. They're transforming experiments.
And on the detection side, catching the light.
Big advances there too. Better cameras, CCDs, CMOS sensors, superconducting detectors that are exquisitely sensitive, even capable of counting single photons in some wavelength ranges, bolometers that measure tiny heat changes. It all adds up to better sensitivity, better resolution, letting us see weaker signals and finer details.
But there's still challenges, right?
Oh, definitely. We always want better resolution, both in space pinpointing where the signal comes from and in time resolving ever faster events.
Oh.
Sample damage is a big one, especially with those intense FEL pulses. You can easily fry your sample if you're not careful. Improving signal to noise is a constant battle. And integrating spectroscopy more tightly with other quantum approaches, simulation, imaging, maybe even direct coupling to quantum sensors or computers, that's a major frontier.
What's the sort of ultimate vision? Where could this all lead?
Well, one really exciting direction is using quantum technology itself to enhance the analysis. Imagine using future powerful quantum computers to analyze the incredibly complex spectral data we can generate.
To model systems we can't currently handle.
Precisely. It could potentially revolutionize the accuracy and speed of interpreting spectra, especially for really complicated molecules or materials.
And AI must play a role too.
Absolutely. Machine learning is already making inroads. AI can be trained to recognize patterns in huge data sets, automate feature extraction from spectra, classify molecules by their fingerprint, maybe even help design better experiments by predicting optimal parameters.
So a combination of better experiments, quantum computation, and AI for analysis.
That seems to be the trajectory. It could unlock a whole new level of understanding.
So wrapping things up, quantum spectroscopy isn't just about measuring light absorption.
Not at all. It's this incredible bridge, really, connecting the fundamental rules of quantum mechanics with the tangible properties of matter we can observe and measure. It gives us deep insights, and it's constantly evolving thanks to new tech.
And its impact is broad fundamental science and practical applications.
Right. Crucial for basic research in chemistry, physics, material science, biology, but also driving real-world solutions in medicine, developing advanced materials, and underpinning the development of future quantum technologies like computing and communication.
It really is amazing, this ability to effectively listen to matter at the quantum level. And thinking about how that capability might be amplified by future quantum and AI tools, it really makes you wonder, doesn't it? It could fundamentally change how we understand and maybe even interact with the world.
It really could. It pushes the boundaries of what we can perceive and potentially what we can control at the most fundamental level. A lot to think about.
Indeed. Well, thank you for this fascinating deep dive today.
My pleasure. It was a great discussion.
And remember, this exploration was based on the excellent essay Quantum Spectroscopy, Präzision auf atomare Ebene by Jur Ovish-Nepetic. A really valuable read if you want to go even deeper.
Definitely recommend it.
And to you, our listeners, thank you for joining us. Goodbye.